Good evening, everyone, and welcome back, this time to the TBAE, the evening public lecture series. I am very proud to introduce you as our plenary speaker, the distinguished quantum physicist, Professor Eugene Polzik from the Niels Bohr Institute, Scientific Director of Danish Center for Quantum Optics, member of Royal Danish Academy of Sciences. Professor Eugene Polzik graduated from St. Petersburg University, as well as received his PhD at this university. Later on, his world line was passed through many universities, in particular through California Institute of Technology, Institute of Photonics in Barcelona, as a distinguished invited professor, and some other places. And finally, in 2003, he became a professor at the University of Copenhagen, the Niels Bohr Institute. Professor Eugene has a number of breakthrough achievements in the quantum domain. In particular, Eugene and his colleagues created a new, very interesting device which acts as a converter ultra-weak radio waves to light, and thus paving very promising applications in the domain of quantum technologies. Professor Eugene is a winner of many awards, such as European Research Council Advanced Grant Award, Gordon Moore Distinguished Scholar Award, Scientific American Research Leadership Award, Danish Society Physical Society Prize, and many others. So it is indeed very difficult for me to introduce Professor Eugene Polzik. There are so many activities. And nevertheless, I want to keep short this from his permission. And today he's given to lead us very interesting area of quantum technology on the road beyond quantum limits, teleportation, and other tricks. Please welcome very warmly Professor Eugene Polzik.
Thank you very much, Professor Lev. Well, it's wonderful to be here again. And I wouldn't call it exactly the public, sort of general public audience, but at any rate, it's good to be simple, right? So we will just try to go ahead and see what is magic and what's not so magic in the field of quantum communication and quantum information science. Quantum puzzles and paradoxes. We all remember that despite all our education in quantum physics, we still are not supposed to understand it in full, but we can believe it because we can predict pretty much so far all the results of the experiments. So, as we know, quantum physics was founded, you say, starting 120 years ago, and then through 1910s, 1920s, 1930s. And then by 1970s, some people actually thought that that's it. We understand quantum physics, we know how to devise equipment, televisions, satellites, all that wonderful business. And even at my home university, the Niels Bohr Institute, people thought that, atomic physics is done, let's look in the nucleus, let's look into the subnucleus. And then something happened. Something happened in the 1990s and further on. And this something was what I called the second wave of quantum revolution. And that happened when the information theory started entering into the physics domain. And what we got from that was the understanding that quantum objects cannot be measured, cannot be copied, exist in superposition and entangled states. And that allowed us to have some real wonders and real, very useful things in the domain of quantum information science and technology. For example, we are promised to have computing with unprecedented speed, and we all remember that every now and then, every few weeks, another big company announces that there is a quantum supremacy and now quantum computers can do something that classical computers cannot do. Then another company would claim that this is not exactly true, but clearly we are going in the right direction, and we will have quantum simulators and quantum computers which will be doing useful things soon. And, 20 years ago I wouldn't say so, but now I think I'm pretty confident that it will happen in a not distant future. The communication with absolute security, this is another holy grail. Everybody is concerned about the communication security, and quantum cryptography promises communication with absolute security, and as a matter of fact, this is a much more advanced field than quantum computing. As we heard and we all know, there are already working quantum communication units, quantum cryptography lines, and in China there is a 2,000 kilometers line, and there are lines in Europe and in the United States and in Russia and elsewhere. And I will not be able to cover the entire field today, but I will try to concentrate on certain basic things and then go further and present you with, for example, teleportation and other things. So a very important part of this business is sensing and measurements beyond the limits that we thought quantum mechanics posed on us only very recently. So the popular part, we understand that light is a wave, which means that if I have a source of the wave and I have two slits, then those two slits can be considered as the sources of secondary waves, and as a result, you will have ripples here, maxima and minima. You can see the same thing if you throw two stones on the water surface, and there will be interference and maxima and minima. What you cannot see when you throw stones on the water surface is what you can see with light, and that is that light is also a stream of photons. And if you do the same experiment, sending photons one by one, what you will see is that initially it's almost indistinguishable pattern. And more you measure, the more you observe the stripes, the maxima and minima, exactly as the wave theory of light will predict. So this duality of light as a stream of photons and as a wave, it sort of underlines a lot of interesting stuff that I will be talking about today. And this is, of course, our favorite animal. And, well, the box is, for experts, it's a little ambiguous. Well, first of all, there is only one cat. And second of all, this is not exactly the Schrödinger cat story, but nonetheless, let's talk about the Schrödinger cat. So what is the big deal about the Schrödinger cat? Well, the Gedanken experiment that Schrödinger thought of, he thought about it in the 30s, 80 years ago, 90, 80. And at that time, it was an absolutely impossible thing to think of. Well, as far as animals are concerned, it's still impossible, but we're growing those cats bigger and bigger. So what's the story? The story is that imagine that I have an atom. Imagine now that I have an atom in two different, as we say, quantum states. And never mind what the quantum states are, but let's say that an atom, as in any quantum object, can be at the same time in two states. It can also be in a superposition of two states. And imagine that in one of those states, this atom will emit some particle, and in the other one, it wouldn't. So if the atom is in a superposition, that means that there will be a superposition of the particle being emitted and not emitted. Now there is a device which is triggered by this particle, and this device kicks with a hammer some poisonous liquid, and because we had a superposition of having the particle and not having the particle here, we have the superposition of the liquid being broken and not broken, and the cat being dead and alive. So why don't we see such cats around? Well, a simple explanation is a cat is too big of an object to create a superposition, and even if there is a superposition, it is eliminated in an absolute split of a second. So it's not a realistic story, but at least it shows you that there are puzzles in the quantum world, and this is completely legitimate story from the quantum mechanical perspective. Now, how big an object can we have nowadays in the lab and still have it in some sort of a superposition? Not like a cat, fine, but let's think of a large object which can still be placed in a superposition of being here and there. And what I want to tell you is that such objects are really getting bigger. So one of the examples that I will be talking about is a gas of atoms, which is contained in this little glass cell. And the gas contains, 10 to the 12, that is million atoms. And even a bigger object, which is this little mechanical drum, which I will show you later in greater detail. And such an object, which you can actually see with your naked eyes, can be put in a superposition of being here and there. Well, here and there is a very short distance, but nonetheless, it is a finite distance. So it all started, as I said, about 90 years ago. And this young man is Werner Heisenberg, when he was visiting Niels Bohr in Copenhagen. And we still have the office of Niels Bohr intact at the Institute. So if you happen to be in Copenhagen, drop by, I'll show you the office. So what Heisenberg figured out was that the world at the quantum level is in principle unmeasurable. There are things that you are not allowed to know about this world exactly. And some of those things are really very kind of simple. For instance, you cannot know simultaneously the position and the velocity of a particle. So what's going on? Like, I always know the position and the velocity of the particle. I take a rock, I throw it, and I know the trajectory. Well, what happens is that if a rock is small, or if you are looking very carefully, then this trajectory becomes blurred. And what happens, to be more precise, is that the uncertainty in the position of an object times the uncertainty in its momentum should be greater than some very small but finite number. It's a small number, but it's a finite number. So if you look carefully enough, or if the object is small, or both, you will see that you cannot trace the trajectory, it becomes blurred. And this is the, in principle, kind of indeterminism in the quantum world. And if you will, this means that we're not allowed to predict the future in all the detail, which is, to me, sounds like good. You know, I wouldn't like to have the future predictable. I'd rather have it unpredictable. So, luckily, our science suggests that this is the case. Another historical photo, Heisenberg giving a lecture at the auditorium where actually we lecture nowadays. And the auditorium has a very interesting blackboard. It consists of many, many layers of boards that you can pull out and push around and close. And the students like to joke that, you know, if you dig deep enough, you will find Heisenberg's handwriting in between. So Heisenberg's favorite example of the, in principle, unpredictability of the quantum world is called the Heisenberg microscope. So here is the story of the Heisenberg microscope. So we have a scientist, and this scientist looks at an object. What does it mean to look at an object? Well, it means that there is light. This light is scattered over an object and gets into the telescope, and then you see the object, or at least the light scattered from this object, right? So you look at me, you see me. Why? Because light is scattered from me to you. So now we're talking about some small object, and we're shining light on it. So what does it mean? It means that light, being at the same time a wave and a particle, goes in and scatters, like this photon comes in, and one of those photons, you know, they can get anywhere, but one of them or a few of them, they get into the telescope, and the scientist observes it. But it's a particle, right? So it's like billiard balls. They collide, and therefore, because this one is bounced out here, the particle gets a little kick. All right, so no problem. We all play pool. We understand how those billiard balls work, except for if we now think that this photon is also a wave, then we're in trouble. Because if it's a wave, and you want to focus it very tightly to see the object, then this wave will also diverge. You know, you focus it, and then it gets defocused. And so, in some sense, you don't know where within this cone this photon went here, and where within this cone this particle is kicked. So now the logic is that we can only tell where the particle was when we had this process of observation. But the result of it is that the particle gets a very ill-defined kick, and therefore you know where it was at this point, but you don't know where it goes. And this is, I think, the simplest and the best demonstration of the quantum uncertainty that I can think of. So the story is that we are not allowed to observe the trajectories of motion of objects with infinite accuracy. Quantum mechanics does not allow us to do it. Of course, for a big object like myself, or even a table tennis ball, or even a smallest particle, you really need to work hard to see this uncertainty. But this little membrane that I showed you a minute ago, this little membrane is good enough so that we actually can observe this process live. We can observe that when we look at this little drum, it begins to move in a chaotic way because we looked at it. And this is sort of like the live demonstration of the Heisenberg microscope principle, and we'll come to that in some time. There are some estimates, like what would happen if the particle has this weight, like some fraction of a nanogram, and what would be the velocity uncertainty. And those are all very small numbers, but they're very good in observations nowadays. So we can actually observe very small displacements and very small velocities. So this is the same little membrane. It's a little bit enhanced in size, but this is 3 millimeters. You go to the lab, you look at this thing, and if I allow you to take it in your hands, then you can actually see it, and you will see this little center. And this little center is the membrane that is vibrating like that. And this membrane is so good that if you knock on it, it will go just like that for minutes. And the frequency of oscillation is 1 million oscillation per second. So it will really oscillate like 1 billion times before it stops. It's a really wonderful thing. Of course, you have to put it in vacuum, because in air, the air molecules will not allow it to oscillate for that long. But vacuum nowadays is not a big deal. So this is an amazing device which we are going to use at some point in this lecture to see how quantum uncertainty and how quantum observation actually happens. Even if you take this little thing and cool it all the way down to the absolute zero, it will still be oscillating. We all remember, hopefully, that the temperature is just a characteristic of thermal motion. What does it mean that I am at 37 degrees centigrade or at 100 degrees Fahrenheit? That means that some atoms in my body are oscillating. And if, God forbid, you decide to cool me down, don't do it. But if you decide to cool me down, then those atoms will start oscillating slower and slower. And the same happens with this membrane. And the point is that even if objects are at absolute zero, they still oscillate. This is what quantum physics tells us, and this is what we see in the experiment, actually. So, admittedly, it's a very small amplitude of oscillations. But you can measure it. We can measure it. And we can prove that even at absolute zero, this membrane still oscillates. So this is another demonstration of the fact that quantum effects are there, and we face them from the fundamental perspective, but also from the perspective of applications. So let's see how this principle works if I want to observe the motion of this membrane. So before, we had this Heisenberg's Gedanken experiment where there was some particle and we shone light on it, and we saw that this thing begins to oscillate, begins to move in an unpredicted fashion. Now we do the same now with this membrane. So suppose I cooled this membrane to the absolute zero. We can do that. So it almost doesn't oscillate. The oscillations are the smallest oscillations allowed by quantum mechanics. And now I want to look at this membrane and measure its position. Looking means sending a photon, reflecting the photon, getting it here. By the same logic that was with the observation of the object, this photon will give this membrane an, in principle, unpredictable kick. And therefore, this membrane that moved little after this kick, or after several photons kicking it, will oscillate more. This chaotic oscillation will be the representation of the result of our measurement. We wanted to measure the position of this membrane very well. Instead, we actually made it moving in a chaotic fashion. And the more we look, the more chaotic it moves. Why is it important? Well, you know, membranes not exactly like that. They are sitting in our mobile phones. They are sitting in geodesic devices. They are sitting in navigation apparatus. Measurement of tiny motion is of utmost importance, as in applications. And if you really want to go to the bottom of the measurement of motion, one day you will hit the quantum limit. And this is what I'm telling you about, that our technology in measurement of motion has developed to the point where the uncertainty due to the quantum measurement begins to play a role. So I told you a little bit about this mechanical motion. Now let me tell you about another interesting quantum object, which can be used, for example, for measurements of magnetic fields. So those two gentlemen, Pauli and Bohr, they are looking at a little spinning top right here. And why are they looking at the spinning top? Because the spinning top is a very nice model of an atom. So electrons move around the atom, and they make magnetic field, and we call this magnetic field a spin, and the spin physics is a big deal in many applications. So this is the artist's view of an atom with electrons around it, and they generate a magnetic field. And the point is that an atom can be simultaneously in two directions of the electron motion, and therefore this atom can simultaneously have its magnetic field or its spin oriented like that or oriented like this. I knew people would wake up at this point. So now we're dealing with a large collection of those spins. And let's see what happens here. So this is a photograph with the artificial color of light passing through a large collection of atomic spins. There is about 10 to the 12 of them. And all those spins are oriented in one particular direction. So you have a large macroscopic vector of spins. And why we worry about it, why we care about it? Well, for example, if you want to measure a very tiny magnetic field, then you want to have a large spin, because then a tiny magnetic field will cause its small rotation, and you will be able to measure this tiny magnetic field. Why is it important to measure tiny magnetic fields? Well, I don't have to tell you about it, right? It's MRI, it's all kind of medical applications, it's all kind of, you know, everyday applications. Again, you know, our phones measure electromagnetic fields. So What is the quantum limit of such a measurement? A quantum limit of such a measurement comes from the fact that if my little spin is oriented in one direction, left-right, then in any other direction it will have a random orientation. And therefore, if I have many spins, then their projection on those two axes will be a random variable. So I'm trying to plot it here. So I look at the first spin in this direction, and I get a minus, and I get another one, and another one, and another one, and in the end of the day, this projection of the spins will have an uncertainty, and this uncertainty will be of the order of square root of the number of particles. So if I have, let's say, 10 to the 12 particles, this will be 10 to the 6. So the angular uncertainty is 1 over a million. It's a small uncertainty, and it's good, but it's an uncertainty which will limit our sensitivity to magnetic fields, and we want somehow to overcome this uncertainty. So how about encoding quantum information in the direction of the spin? That sounds like a good plan, because those spin systems have reasonably long lifetime. You can encode quantum information in it and then maybe transfer it. So let's say that I want to encode 3 different numbers into the direction of the spin. So this will be one direction, this will be another direction, this will be a third direction. But notice that if the uncertainties of those spins overlap, like I have it here, then you cannot distinguish between those 3 directions in a measurement, right? Because the uncertainties overlap, so you measure something and you don't know which of those 3 you had. Nonetheless, with the principle of teleportation, you can transfer this unknown quantum state onto another spin and recreate it from here to there. So the principle of teleportation allows you to transfer an unknown quantum state without looking at it, and if there is some secret information encoded in this state, it will be transferred intact if you don't look. If you start looking, then you're in trouble. So this is what I just told you. And let me spend the next 10 minutes on the teleportation. So this new quantum type of communication called teleportation requires some very special quantum states called entangled states. And we will see in a second what this is all about. So another historical excursus. Back in 1935, Einstein, Podolsky, and Rosen came up with the example of entangled states. So they said, suppose we have 2 particles at a large distance, and one of them has the position and the momentum, and the other one has the position and the momentum. And quantum mechanics allows us to know the distance between those 2 and their total momentum. So we can know the distance exactly, and we can know the sum of the momenta exactly. And those 3 gentlemen, well, unfortunately, I couldn't find the photograph of Podolsky, so it's only Einstein and Rosen. I'm sure he looked that way. So what they didn't like about this was that if I'm sitting on planet Earth and you're sitting in the other constellation at a zillion kilometers, then I, by my free will, can decide whether I measure the position of my particle or whether I can measure the velocity. If I decide to measure the position, then I immediately know the position of your particle. And this happens faster than the speed of light. On the other hand, if I decide to measure the momentum or the velocity, I immediately know your momentum or the velocity. So it looks like by my free will, what I want to measure here, I will project your state, so to say. I will define your state of your particle, either as a state of the position or as a state of the momentum. And Einstein, Podolsky, and Rosen couldn't stand it, because they couldn't have anything propagating faster than the speed of light. What we know about this paradox today is that this is true to the best of our knowledge, but at the same time, it does not allow transfer of information faster than the speed of light. And we will see in the teleportation protocol that you can transfer states of objects, but you cannot do it faster than the speed of light. So, my favorite example of two entangled macroscopic objects is obviously from our own work. And this is a nice pictorial representation of this entanglement. So I told you about a macroscopic spin, and we have two systems, each of them represented with this large macroscopic spin of those atoms. They are oriented in opposite directions. Each of them has a large uncertainty, but the pictorial representation of an entangled state is a superposition of all anti-parallel directions. So you don't know which direction each of those spins points, but you know that if you find this one in that direction, you will find another one in the direction exactly opposite. And if you measure this one here, then you will find that one like that. So they are always exactly anti-parallel. And this is the representation of an entangled state, and this is what we have demonstrated some 18 years ago in the experiment. So this is an entangled state, and now we can use it to perform a teleportation, for example. So what's the problem with teleportation? It's difficult to send matter long distance, right? So we all know and love Star Trek, and they all do like here and then there. Well, the thing is that you cannot send matter with the speed of light, even closer to the speed of light, and you don't have to. So let's not send material objects. Let's just send instructions how to build the material object. So, you know, you are complex creatures, but in principle, information about you can be read and written down as a set of instructions. And if on some other planet you have a pile of garbage, which will contain all the atoms required to recreate you, then what the problem is? You know, you call on the phone, you send instructions, you build your copy. Well, I don't know about you, but quantum objects cannot be represented like that. And the reason is, you cannot learn everything about the quantum system. I just, spent half an hour explaining to you that we cannot measure the position and the momentum at the same time. By the same token, you cannot measure the position and the momentum and spin of electrons and other quantum particles. So this is not allowed. As soon as you look at me, in principle, you change me. So we need some tricky way to do it. And here is a very pictorial way of how to do it. So let's take Einstein. We want to teleport him. We have two piles of atoms here and here, and they have enough material to build this gentleman, if you have sufficient instructions. So what you do is you first create an entangled state between this pile of material and this pile of material. Don't take it literally, right? So this is kind of an example. It's a science fiction example. I will give you later on the scientific example, but don't take this literally. But the principle is there. You take this pile of material and poor Albert, and you make a joint measurement on them. Ba-bam. As a result of this joint measurement, you wipe off poor guy, and you completely destroy the state of this pile, and as a result, you get a string of numbers. Now, this string of numbers is an instruction set. You send it via radio waves, for example, to another planet, and using those instructions, one can recreate from this pile Einstein, if the fidelity of teleportation is good. If not, well, maybe it will be Bohr. So, two important ingredients for teleportation: the creation of entangled state at a distance between the sender and the receiver, joint measurement, and classical communication. So immediately from here you already see that this process can not go faster than light. Why? Because you need to send the set of instructions. And those classical instructions cannot propagate faster than the speed of light. So this process of teleportation cannot happen faster than the speed of light. That's good news. So let's just look in a little more detail how this thing works for mathematically oriented people. But seriously, this math, you should be able to reproduce it after this slide. So we have two entangled objects, one with the position x1 and the momentum p1, and the other one x2 and p2. And they are in the entangled state. This is on planet Earth, this is on planet Mars. They're in an entangled state, meaning that you know exactly the distance and you know exactly the total momentum. Now you have your Einstein, the third particle, which you want to teleport here. This particle has an unknown position and unknown momentum. And now you do your trick. You make a measurement which is allowed by quantum mechanics. You make a measurement of the x1 minus v xv and p1 plus pv. And for those mathematically oriented, it's obvious that you are allowed to make a measurement of the distance and of the total momentum here, because they commute, again, for physicists. What you get as a result are two numbers. The objects are wiped off by this measurement, by this quantum back action, but we don't care. Now we take those two numbers and send them on planet Mars. And now watch my hands. I take x2 here and I subtract this number cx. But the cx is x1 minus xv. So when I subtract it from here, I get x2 minus x1 plus xv. But x2 minus x1 is 0. So you get xv here. Okay? Any objections? Well, there could be objections, but let's wipe them under the carpet. So, with this extremely simple arithmetics and a little bit of quantum mechanics, you realize that you can perform a transfer of an unknown quantum state two variables which you are not allowed to know, but you are allowed to transfer. Two important things. One is that you cannot make several copies, because entangled state is a monogamous state. You can only entangle me with one woman, not with many. Therefore, the cloning is not possible. And another thing is that it cannot happen faster than the speed of light, because you need to send classical information. So now you can go back home and tell the story of teleportation to your children. You'll get a lot of credit for it, trust me. Well, from now on, it's going to be wing flapping and singing and dancing, because of course, yes?
Further, can you explain what you mean by wiping out the particles?
Right.
Suppose they are fundamental particles like electrons.
Right. So what wiping out means that as in the process of this measurement, I impose quantum back action on both of those two. And it so happens that this quantum back action is random, and therefore the position and the momentum of this particle and this particle is completely randomized.
The particle is still there.
The particle is there, yeah, it's right. I mean, again, we're not sending any masses anywhere. We're sending information, right?
Excuse me.
Yes?
Second information is also material process. You cannot say that it is not material. Right?
Sure, right.
So still you need a particle.
Yes, you need energy to be sent, absolutely true, that's right. So in this experiment, we performed the poor man's version of teleportation of Einstein. So we had those two atomic objects. We send light, so a pulse of light here. We send it through one, we send it through the other. We make a measurement. We send the result of the measurement here. And as a result of this process, you publish a paper in Nature. Because you demonstrate that you have teleported the state of the spin from here to here. This distance was, as you can see, 40 centimeters, but it could just as well be a kilometer. So what we actually teleported was something funny. So I told you about this direction of the spin. We teleported the unknown trajectory of this spin. So we programmed this spin to make this kind of little trajectory here on this surface. And now this is the trajectory of the object of teleportation. And if I wouldn't show you this red line, you wouldn't have guessed what it was, because there is a lot of quantum uncertainty. All those gray dots is exactly what we had there. And as a result of teleportation, we pretty much kind of sort of recovered the trajectory. It's not 100%, but it's good enough to claim that it is quantum teleportation. So you can teleport the direction of the spin. You can encode secret information in this direction of the spin. You can encode the measurement of some tiny magnetic field or whatnot. And so the thing works. Yes. So at some point, even CNN looked at us, but that was some time ago. Right. I think I actually should slowly wrap up. So this last part, I will really walk you through it very quickly. And it will be again about the measurement. And as those of you who attended the morning lecture remember, there are classical trajectories, there are quantum trajectories, and sort of people who thought of the reference frames and people who thought of quantum uncertainties taken together tell you that it is impossible to make a measurement of the particle motion. And what we're trying to say is that if we do some little tricks with this so-called negative mass reference frame, you can make a measurement beyond quantum limits. And again, what you need to do is an effective negative mass reference frame, and I don't have time or desire to tell you what this is. You need an entangled state, which you have seen before, and then you can do your tricks. And I don't know if you want to make an effort at this time of the day. Should we? Should we make an effort? Are you ready to make an effort? Is it a yes?
Yes.
Excellent. So, this is the position of my particle as a function of time. I had a wonderful photo here of girls and boys at school, but then I decided to delete it. But this is what happened to all of us in the 8th and the 9th grade. This is the position as a function of time. It's the position at time 0 plus the derivative of the position over time times time. This is the velocity, right? So this is x naught plus vt. Does it ring the bell? Maybe. So the point is that from the quantum perspective, this object and this object, the momentum and the position, they cannot be measured simultaneously. Therefore, I cannot have the trajectory well defined because, as we agreed, it will just diverge. Either I know the position initially or I know the momentum initially, but not both. And now the next portion of the arithmetics. Now I make a measurement of the position in the reference frame, which is attached to an object with a negative mass. And so this difference is the initial difference of the positions plus the difference of the velocities times time. And if we go further, then we again see there is a difference between the positions and the difference between the two momenta, and we are not allowed by quantum mechanics to measure them simultaneously. Except for if I take a negative mass of my reference frame, then I change the sign here, and now I have the difference of the position and the sum of the momenta, and Einstein, Podolsky, and Rosen told us that we can measure those two things, and therefore, in the reference frame associated with a negative mass object, I can make a measurement of my motion with, in principle, arbitrary accuracy. So I think the second time it kind of sinks better than the first one. Right, so we did the experiment. It was published in a reputable journal, so that must be true. I don't have time to tell you about it. It involves the two objects that we talked about, the moving membrane and the moving spin, and we demonstrated the first baby step towards observing this motion in the reference frame of this negative mass object. Yeah, so life is good, very good, excellent. So this is what made us published in Nature, whatever it means. And again, the final few minutes, once again, the story about gravitational wave detection meeting quantum mechanics. So once again, will remember 3 years ago the Nobel Prize was given for observation of gravitational waves. And this is the device that is used to measure the gravitational waves. Those are vacuum channels, 4 kilometers long, 2 of them, one in Washington state, another in the state of Louisiana. And when the gravitational wave comes, it shakes the mirrors which are hung in the end of those channels. And those mirrors, so this is the picture of this interferometer, 4 kilometers here, 4 kilometers here. So the gravitational wave comes and shakes this mirror and shakes this mirror. Like that. And as a result, you have a signal. This is a signal, and this signal earned them the Nobel Prize. It's an incredibly weak signal, unbelievably weak. It changes the distance by 10 to minus 21. We're dealing with small numbers, but this is just unthinkable. And yet, people can measure those things, and it's amazing. But what's more amazing is that the sensitivity and precision of this measurement is now limited by one single thing, and that is quantum fluctuations of those mirrors. You send light, there is like 100 kilowatt of laser power, those photons bombard those mirrors, and they start shaking them, and they shake them to the extent that you cannot see gravitational waves very well. So you must somehow go beyond this quantum limit that I just told you about for an hour. And here we come, nice and pretty, and we say, let's take our little atomic gas, put it somewhere here, and make a joint measurement, and give us funding, we will give us your solution. So this is the experiment in progress. This is my co-worker, Farid Khalili, with whom we proposed this thing. And essentially, this thing shows you that this is this 10 to minus 21 sensitivity of the measurement of the distance in the interferometer. And this is where they are. And this is where we tell them they might be if we are successful with our technique. So you can improve the sensitivity of gravitational wave observation by a factor of 2, increase the size of the universe that you can observe in this way by a factor of 8, and live happily ever after. So, to continue and finish, this is where I started. I haven't covered the whole map, of course, but I tried to tell you about some fundamental puzzles of quantum physics and some ways to overcome certain limits that we thought were unbreakable even 20 years ago. You are great. Thank you very much for your attention.
Questions, please. Yes.
My question actually is related to EPR paradox. I'm not specialist in relativity, so maybe you or somebody who is here can teach me. So, as far as I understand, there is some principal contradiction explanation of EPR paradox, because the EPR paradox itself is formulated in the frame of classical, not classical, how to say, standard quantum mechanics. That is not relativistic. For that reason, sometimes it cannot cover the phenomena coming from the limitation of transferring of information with the speed of light. So is there any attempt to extend, not to extend, to reformulate EPR paradox in the terms of quantum field theory, and maybe as soon as it will be reformulated in quantum field theory, there is no any paradox at all? I mean, do you know such?
I am not aware of such things, and you know, I am not an expert in relativity either, but I seriously I haven't heard about it, and I'm sure I would have heard about it if it would have existed. So the answer is no.
So for completeness, can you also maybe say a few words about your ideas on time energy uncertainty? Because it's a different setting, so it is not exploitable to teleport energy, for example, as we do for the external.
So to me, the time-energy uncertainty is simply the uncertainty between the frequency and timing. So imagine that I want to transfer a lot of information over optical fibers. So how do I do it? I want to pack as many frequencies as possible, very close by in the multi-channel, and I want to use not too many photons sort of per channel. And then quantum physics tells me that there is a limitation, given the number of photons in the pulse that I want to receive, there is a limitation on the minimal bandwidth of this communication that I can use. So that's sort of the uncertainty principle limitation on the classical communication, if you wish.
This is really interesting. So we get a factor of 2. So is there a way we can get another factor of 2 if I can somehow have some kind of chain of along the lines of your scheme, or is this really the end perspective too?
No. The factor of 2 is a question of money. There is no other limitations. So, well, I mean, there are other limitations. I wouldn't promise you a factor of 100, but the difference between a factor of 2 and a factor of 10 is money.
And what does that money do?
This money buys you superb optics. It buys you 10 engineers to design your system and optimize it in all possible ways, instead of 3 graduate students working days and nights. So the hope is essentially that if we can show on our breadboard a factor of 2, then somebody would say, oh, Eugene, just, spend the money. Don't limit yourself. This is sort of half serious, because in fact, the interferometer itself, it has optical losses. So essentially, I'm pretty sure that if they would like to use any of those tricks, they would have to work on their optics. But they have unlimited resources, so no worries there.
So, if no other questions, please let us thank you.
Thank you.